Hello. With this video, we begin our study of chemical kinetics. Chemical kinetics is the study of the rates of chemical reactions, and in the first section, we're going to talk about what a reaction rate is. The reaction rate is defined as the change in concentration of reactant or product per unit time. So for the generalized reaction, 1 mole of A reacts to form 1 mole of B, we can calculate an average rate over a time interval by subtracting the concentration at time t1 from the concentration at time t2 and dividing by t2 minus t1. So that's the change in concentration divided by the change in time. I will express that as negative change in concentration of A over change in T, which is equal to the change in concentration of B over the change in T. Because the concentration of A is decreasing, the change in concentration of A is negative, but by convention, reaction rates are always positive quantities, hence the negative sign before delta A. So our goals are to develop and apply quantitative models, that is equations, for how the rate of reaction depends upon the concentration, how the concentration depends upon time, and how the rate of reaction depends upon temperature. So the big question is why? Well, you'll see later in the unit the reason is, if we understand how the rate of reaction depends upon concentration, we can very often obtain information about reaction mechanisms, the precise pathway on going from reactants to products. Now, I use the word pathway because we spent a lot of time in Chapter 6 talking about how state functions or state properties are pathway independent. And I believe I showed you this diagram, and I'll show it to you again. Here we show a reaction progressing from reactants to products. It's a potential energy diagram. We said that thermodynamics only depends upon the initial and final states. That is, all we care about are the relative energies of the reactants and products, and that is true. Kinetics is concerned with the pathway. We don't particularly care whether the reaction is endothermic or exothermic. What we care about is the precise set of steps on going from reactants to products, because that determines the rate. So, let's take an example. Nitrogen dioxide decomposes to form nitrogen monoxide and oxygen gas. If we start with a flask containing only NO2 at a certain temperature, allow the reaction to progress, and then measure and graph the concentrations of reactants and products as a function of time, we would obtain something that looks like this. So take a moment, pause the video, and see what you see. The concentration of NO2, represented by the green line, we can see starts at 0.01 molar and decreases with time in a nonlinear fashion. We see the concentration of NO, represented by the blue line, increases with time in a nonlinear fashion. And we also see that the concentration of O2 increases in time in a nonlinear fashion, but not as fast as the concentration of NO is increasing. What you'll notice is that the curves showing the decrease in concentration of NO2 and the increase in concentration of NO are inverses of each other, and that makes sense because NO is being formed at the same rate that NO2 is being consumed. We also see that the rate of production of O2 is only half as great as the rate of production of NO, and that's because of the stoichiometric coefficient. I only have 1 mole of O2 being formed for every 2 moles of NO being formed. Okay? Now, let's talk about the rate of reaction. Okay? We'll define the rate of reaction as the decrease in concentration of NO2 with respect to time, which is equal to the increase in concentration of NO with respect to time, which is equal to twice the increase in concentration of O2 with respect to time, again from the stoichiometric coefficient. Okay? We can calculate the average rate of reaction over a time interval, and so let's say the change in NO concentration over change in time. Let's take the first 50 seconds. In the first 50 seconds of the reaction, the concentration of NO2 drops from 0.01 mole to 0.0079 moles. That's negative 4.2 times 10 to the negative fifth mole per liter per second, but again, because rates are always defined as positive quantities, the average rate of reaction over that initial 50-second time interval is 4.2 times 10 to the negative fifth moles per liter per second. That's an average rate over a time interval, but the instantaneous rate would be the slope of a line tangent to the curve at any point, and what we can see is that as the reaction progresses, the rate of reaction is decreasing. Okay, so let's calculate an average rate of reaction over 50-second time intervals. As we said, second time interval, it's 4.2 times 10 to the negative fifth mole per liter per second. But for the second time interval, it's slower, and it goes progressively slower and slower. Why is the rate of reaction decreasing with time? Well, As the reaction progresses, the concentration of NO2 decreases, so therefore we must conclude that the rate of reaction in this case is a function of concentration of reactant. As the concentration decreases, the rate of reaction decreases. The rate also depends upon the concentration of products, but we're not going to be concerned with that. So let's do an example where we calculate the reaction with respect to relative to different components in the reaction. In this reaction, 4 moles of phosphine gas decompose to form 1 mole of phosphorus gas and 6 moles of hydrogen gas. If in a certain experiment over a specific time period, 0.0048 moles of pH3 is consumed in a 2-liter container for each 1 second of reaction, what are the rates of production of P4 and H2? Well, the first thing I'm going to do is use the given information to calculate the rate at which pH3 is being consumed. So my change in concentration of phosphine with respect to time is equal to the moles of phosphine consumed divided by the volume of the container divided by the time interval, 0.0024 moles pH3 per liter per second. I can use that to calculate the rates of increase of concentration of P4 and H2 simply by taking the rate of reaction that I just calculated and applying mole ratios. Notice I'm using formulas in my rate units. So to calculate the rate at which P4 is being formed, I'll take my 0.0024 moles of pH3 per liter per second and then simply multiply by a mole ratio, 1 mole of P4 for every 4 moles of pH3 to calculate the rate at which P4 is being produced. And I'll do the same thing to calculate the rate at which hydrogen is being produced, take my rate of consumption of pH3 and multiply by the mole ratio, 6 moles of H2 produced for every 4 moles of pH3 consumed to get the rate at which hydrogen is being produced. Let's do another example. At 40 degrees Celsius, hydrogen peroxide decomposes according to the following equation. The following data were collected for the decomposition over time. We start with 1 molar H2O2. After 21,600 seconds, that decreases to 0.5 molar. And after 43,200 seconds, that decreases to 0.250 molar. So let's calculate the average rate of decomposition of hydrogen peroxide for the first time interval and use that result to calculate the rate at which oxygen is being produced. So once again, I will subtract my initial concentration from my final concentration, divide by time. That gives me 2.31 times 10 to the negative 5th moles of hydrogen peroxide per liter per second. And to calculate the rate of production of O2, again, I'll take the rate of consumption of hydrogen peroxide and multiply by a mole ratio. What is the average rate of decomposition for the second time interval? And from that, what can we conclude about the dependence of the reaction rate on concentration? I'll do the same calculation, and now I see for the second time interval, the rate of reaction is actually decreased substantially. So we see that because as the concentration of H2O2 decreases, the rate of reaction decreases, we conclude that the rate of reaction does depend upon concentration. Now let's talk about rate laws. So how quantitatively does the rate of reaction depend upon the concentration of reactants? We will express that by using what is called a differential rate law, or sometimes just rate law, which is a mathematical expression that shows how the rate of reaction depends upon the concentration of reactants. A rate law for the hypothetical decomposition of A to form products always looks like this. The rate, which I will define as the decrease in concentration of reactant A with respect to time, is equal to K times the concentration of A to the n power. K is called the rate constant. It has a specific value at a given temperature and it has specific units. N is the order of reaction with respect to reactant A, and it is very often either 0, 1, or 2. There are other examples of different orders of reaction, but we're only going to deal with reactions in which N is 0, 1, or 2. Now, there is another form called the integrated rate law. The differential rate law shows how rate depends upon concentration. The integrated rate law shows how concentration depends upon time. Both of these are extremely useful. And if you have taken calculus, or if you're in calculus now, you know that to go from the differential rate law to the integrated rate law, you carry out a process called integration. Or to go from the integrated rate law to the differential rate law, you carry out a process called differentiation. If you have not taken calculus or are not in calculus, don't worry. You don't need to understand any of this because it is all given to you. The beauty of this is that for a given form of the differential rate law, there is a specific corresponding form of the integrated rate law. So once you know one, you automatically know the other one. So our goal is to learn how to determine one or the other experimentally, and which you choose, either the differential rate law or the integrated rate law, depends upon experimental convenience. And once again, once you have the differential rate law, that can often give you insight into the reaction mechanism. So let's finish up by talking about units on rate constant. The units on the rate constant will depend upon the order, and as you'll see, there is a very specific pattern. So state the correct unit for each of the following quantities, assuming the concentrations are in moles per liter and time is in seconds. Just as an aside, concentration doesn't have to be in moles per liter. It could be partial pressure in atmosphere. Time doesn't have to be in seconds. It could be in minutes or hours or days or years. But in this case, we're going to choose molarity and seconds. So the rate of a chemical reaction using these units is always moles per liter per second. To determine the unit on the rate constant for zero order rate law, well, I'll write out my zero order rate law. The rate is simply equal to K times the concentration of A to the 0 power, which is 1. For a zero order rate law, the rate of reaction is constant. The rate is equal to the rate constant. Therefore, the unit on the rate constant is simply equal to the unit of rate, mole per liter per second. For a first order rate law, where the rate of reaction is equal to a rate constant times the concentration in moles per liter, well, I can simply ask myself, what must the units on K, the rate constant, be so that things cancel and I get the correct unit for rate, which is mole per liter per second? So I'll set it up like this. Since A is in moles, concentration of A is in moles per liter, and rate is in moles per liter per second, the unit on a first order rate law, the unit on a first order rate constant must always be reciprocal time, in this case 1 over seconds. Older textbooks actually call that the reaction frequency because frequency, you know, is reciprocal seconds. Really old textbooks call the unit hertz, but we're not going to do that. For a second order rate law, in which the rate of reaction is proportional to the concentration of A squared, now in order to get units to cancel to give me moles per liter per second, the unit on the rate constant must be liters per mole per second. Correspondingly, for a third order rate law, which is extremely rare, but we can talk about it as a hypothetical case anyway, in order for the units to cancel, the unit on the rate constant must be liters squared per mole squared per second. If you look at these, you see a pattern. To generalize, for an nth order rate law, the unit on K is liters to the n-1 divided by moles to the n-1 per second. Okay, in our next video, we will talk about how we determine the rate law.